In my last video, I walked through the setup of these DGX Spark-style devices and compared them to a Mac Studio. Today I'm going to connect two of them together using a ConnectX 7 port, and this will allow me to run larger models like MiniMax 2.7, which is a 230 billion parameter model. Another benefit of connecting multiple Sparks together is you can typically increase the token per second rate on smaller models. Okay, let's start by looking at the hardware. I'm using two different variations of the DGX Spark. The first is a Gigabyte AI top atom, and the second is an ASUS GX10. They're essentially identical, but I wanted to show that you can mix and match the different variants with good results. The cable I'm using is kind of interesting. It's an ASUS branded QSFP112. It's rated for 400 gigabit per second, but the DGX Spark uses half that amount. Based on the end caps and the release straps, it looks like the cable was manufactured by Amphenol. By the way, the Q in QSFP stands for quad, as in 4 independent transmit and receive channels. This is easier to visualize if you look at a breakout cable. Here's one that I found on a website where a single QSFP112 connection breaks out into 4 100 gigabit cables. If you've never used an SFP style cable before, they just slide in and lock into place. In the case of my cable, you just use this strap to release the internal clip to pull them out. I'll be connecting both ends to the left ConnectX 7 ports on both machines, and this will be the 0 interface. Connecting two Sparks is an exercise in networking, so I want to take a deep dive into how that works. On my machines, I have 3 networks running. First, I have a Wi-Fi network that connects to my internet gateway from my ISP. This is a 192.168.1 network. The next network is a 10 gigabit Ethernet, and I'll use this network to connect to my laptop and maybe a Kubernetes cluster down the road. By the way, instead of using Wi-Fi, you could put a router in front of the 10 gig network and route to the internet that way. The Wi-Fi was just easier in my case. Finally, we have the ConnectX 7 network, and here's where things start to get interesting. As you can see, there are 2 networks for each ConnectX 7 port, with 2 MAC addresses and 2 IP addresses, which are bonded together. It's a little strange, and to understand why, we have to take a closer look at the GB10 chip. On the far right, we have this blue strip called the high-speed I/O, and it's where all the PCIe devices come in. The interesting thing about the GB10 is each device is limited to 4 PCIe lanes, which is about 100 gigabit per second of throughput. And that's going to be a problem because the ConnectX 7 ports are 200 gigabit per second devices. So to reach that throughput, 2 PCIe devices had to be bonded together to create a single port. And that's why you see 4 interfaces instead of 2 once you connect everything up. One thing that was surprising to me is it's kind of hard to find detailed information about the high-speed I/O on the GB10 chip. The best resource I found was this website called Serve the Home, which had a really nice write-up about the PCIe and ConnectX 7 architecture. I highly recommend checking it out if you want to do a deep dive into the topic. Another interesting thing about the ConnectX 7 port is it uses something called Remote Direct Memory Access, or RDMA, instead of TCP/IP. I found a nice diagram on the FS website that outlines the differences. You can see here that RDMA bypasses the OS and kernel that's usually used for network operations. RDMA was designed for high-speed communication in data centers where you control the environment. On the other hand, TCP/IP was designed for resiliency and can handle things like rerouting if a squirrel chews through the fiber optic cable. There are a couple of different networking stacks that can be used with RDMA, and this is where things get a little bit confusing. Here's a table from that same FS website that shows the differences. IB or InfiniBand is an open standard with proprietary hardware. On the left is a full stack using InfiniBand hardware and messaging. The DGX Spark uses RDMA over Converged Ethernet version 2. The acronym is pronounced RoCE, and RoCE uses Ethernet hardware with InfiniBand messaging. That's why some of the networking utilities you'll use contain IB in the name. Okay, now that we understand the networking, let's get this thing running. The initial setup is outlined in two of NVIDIA's playbooks. The first one is called Connect 2 Sparks, and just click on the Run on 2 Sparks tab and then follow the instructions. For me, everything worked well and I had no issues, but let me give you a high-level overview of the process. First, you want to create the same user on both machines, and next you want to set up networking. Since this is Ubuntu, the networking is configured using Netplan. I decided to use option 2 and create my own Netplan configuration files. And I use the same IP addresses described in the playbook. You'll want to do this on both machines. Remember I mentioned InfiniBand earlier? Here's an IB command to view the interfaces. You should see two that are in the up state, and these are the two logical interfaces that I talked about in the networking section. Next, you'll have to set up some static routes on both sides to point to each device. Finally, you'll have to set up SSH for each machine and copy the public key to the authorized file on the other machine. This will allow SSH to connect without prompting for a password, and this will become important for the serving engines later on. To get this going, you can either run a script provided by NVIDIA, or if you're familiar with SSH, you can set it up manually. In my case, I just used the NVIDIA scripts, which worked out fine. The next playbook we'll have to set up is called NCCL for 2 Sparks. Again, we'll click the tab on the page to view the instructions. Just like the last playbook, the instructions were pretty simple and worked out well. But instead of walking through all these commands, I want to explain what NCCL is and why it's important. NCCL, pronounced nickel, stands for NVIDIA's Collective Communication Library. Remember when I talked about how RDMA bypasses the OS kernel and CPU? In the case of our DGX Spark, nickel is what makes that possible. It sets up GPU CUDA kernels, which allow for memory-to-memory transfer, so it's very important that you set up this playbook on both machines. Okay, with the initial setup out of the way, let's start to serve some models. I'll start with one of my favorite projects from GitHub called Uger Spark vLLM-Docker. Just like the name implies, it wraps vLLM into a Docker container, and it has lots of nice recipes to make serving models easier. If you see my last video, the setup is very similar. First you clone the repo, then change into the working directory, and run a script called building copy. Except this time, you want to use the -c argument. The purpose of this script is to create a Docker image, and the -c argument will use the connectx-7 ports to auto-detect the other machine and copy the image over. Before we run the recipe, we have to decide how we want to download the model. We could just run the recipe and let it download the model for us, and this will work, but the issue is with this approach, the model is downloaded twice from Hugging Face, once for each machine. A better approach is to use a script in the repo called hfdownload, which will download the model once and then copy it over to the other machine. You can also manually grab an image from Hugging Face and then just tar it up and copy it over using rsync or SCP. Okay, with the model downloaded, we're finally ready to run the recipe. For this video, I'll run two. The first one is called MiniMax 2.7, and it's a model with 230 billion parameters, which is too big for one Spark. So it's a good test case. To get it going, just launch the run recipe script with the name of the recipe. After a few minutes, the model should be running. Here's a simple prompt to get things going. And with this model, I've been getting roughly 40 tokens per second. The next model I'll try is Nemotron 3 Super. This one is interesting because it already runs on a single Spark, but running it on two should give us a faster inference speed. Again, running the run recipe script gets things started. And I'll use the same prompt to get things going. You can see I'm getting about 25 tokens per second with this model, which is almost double what I get from a single Spark, which is about 15. So at this point you may be thinking, this is great, but how are these large models being split between two machines? I mean, how does this even work? And to answer that, I want to talk about two settings in vLLM, tensor parallel size and pipeline parallel size. here's a conceptual diagram of a simple large language model to help us out. Pipeline parallel size splits the layers between machines and can run using slower network connections. Tensor parallel size splits the tensors within layers called shards, which are processed by different machines. There is a lot of communication required for this approach, so it requires fast networking to make it feasible. And since the DGX Spark has fast 200 gigabit networking, it typically uses the tensor parallel argument to split the models between machines. With all these shards, we need a way to keep track of where everything is and to consolidate the results. Typically, a distributed framework called RoCE is used to handle the orchestration. And Nickel, that we mentioned earlier, handles the consolidation and the calls to the CUDA kernel and memory. Okay, I think that's enough for today. And by the way, if you're running 2 or more of these things, let me know in the comments what your experience has been. Until next time, thanks for stopping by, and I'll see you in the next video.